Alright, so in today's video we're looking at a review and overview of the first unit of grade 12 chemistry. The unit was called Electronic Structure, Bonding, and the Periodic Table. It began with a discussion of the nature of light, and that's because it turns out that light has both properties of waves and particles, and that provided the springboard to discuss the new model of the atom, in which electrons also have wave and particle properties. So we began with looking at things like wavelength and frequencies of light, and there were calculations involved with that using the formula C equals lambda nu. Wavelength times frequency is the speed of light. We then knew the different regions of the electromagnetic spectrum, from gamma radiation all the way down to radio waves, and we were able to rank things like wavelengths and frequencies and energies for the different regions of the EM spectrum. We resurrected the particle theory of light when we looked at Planck's equation. His equation gives us the energy on one quantum or one particle of electromagnetic radiation. His equation for that energy says that the energy is proportional to the frequency of the light. So E equals h nu, where h is Planck's constant. That equation could also be written as E equals hc divided by lambda, where lambda again is the wavelength. Right now we're starting to see the bizarre nature of the world around us, because Planck's equation involves wave properties, frequency and wavelength, to explain the energy on particles of light. So we then moved on to take a look a little bit more deeply at the Bohr model of the atom. We had an equation with the Bohr model for finding the energy of electrons in different energy levels. Using that equation and Planck's equation, we could do things like this. We could calculate energies, wavelengths, frequencies of light, electromagnetic radiation, emitted when electrons fall from higher levels to lower levels in single electron species. The most common example of that would be hydrogen, but also helium, which has lost 1 electron, so He positive, or lithium, which has lost 2 electrons, Li2 positive. If you have a 1 electron species, Bohr's energy equation works. We then left the Bohr model of the atom and we began looking at the newer model, the quantum model of the atom. And in there we had energy levels, sublevels, S, P, D, F, and a whole lot of complexity to that. We defined orbitals as regions of space in which the electron can be found around the nucleus, and from there we ended up drawing orbital diagrams, electron configurations, noble gas abbreviated configurations, and valence electron configurations. In other words, we depicted where electrons were in this newer model of the atom for different elements. There were several names that were very important in this model. The Bohr, this old model, but Bohr also helped develop the quantum model. Heisenberg gave us something called the Heisenberg uncertainty principle, which is at the heart of the new model of the atom. Schrödinger gave us the wave equation, Schrödinger's wave equation, from which orbitals are pictured. Pauli gave us the Pauli exclusion principle, which limits the number of electrons there are in one orbital. And Hund gave us a rule for filling orbitals of equal energy. He said that those, when filling them with electrons, you have to keep electrons unpaired as long as possible. Alright, we then moved on to look at the periodic table and various trends and properties. We saw trends in ionization energy, first ionization energy, trends in atomic radius, and electronegativity. We need to know what those things mean, as well as be able to use them to predict whether an atom has a larger radius or a smaller radius than another atom, etc. We also discussed successive ionization energies, so not just the first, but a second, third, fourth, etc. ionization energy for an element. Finally, we discussed bonding very quickly, and we realized that covalent bonding from our grade 11 course is a little bit more complicated because there's 2 types, polar and nonpolar covalent bonding. We came up with a better way to define these 3 types of bonding using electronegativity values. Alright, so you're going to have access to your data booklet in the test, so be sure you're familiar with the data booklet. You've done lots of homework problems. You know that on the inside cover there are important formulas that we use a lot. In the atomic structure unit or section, there's the formula C equals lambda nu, Planck's energy equation. We're not going to use de Broglie's wavelength equation, but we did discuss it briefly. And then there's Bohr's energy equation that we mentioned just a minute ago. We also have in the data booklet, if you need them, if you forget them during the test, there's a table on the next page of constants. And in here, the very first constant is the speed of light, so there it is. And further down, you'll find Planck's constant, which is another constant you'll need in using Planck's energy equation. And finally, you remember at the bottom of this second page, there are those prefixes, so if during the test you encounter something that says nanometers or millimeters and you forget exactly what the prefix means, there are these factors here which help with our calculations. Alright, so if you've got your data booklet, you might as well keep it open either to the formula sheet, or we'll need later the table of electronegativity values, so you might want to have it open there. I'd strongly recommend that what you do to make use of this review is not just watch the video. If all you're going to do is watch the video, it's going to be of limited value to you, but rather pause the video, try the questions yourself, and then check your answers. Feel free to skip through the video to different questions in which you need some extra practice. You don't have to sit there and watch the entire thing from start to finish. So this first question, we're starting with the nature of light. We have here pictured some electromagnetic radiation, and we're asked to find the frequency and the energy of the radiation. In the picture, we're told that the distance from here to here in the radiation is 426 nanometers. Now, looking at that, the way that's pictured, the distance from this trough to this trough in the wave, that would be one wavelength. The distance from this trough to the next one is another wavelength. So that distance, 426 nanometers, is actually two wavelengths. So if we take 426 nanometers and divide by 2, we get 213 nanometers, and that's the wavelength of that radiation. Remember, the Greek letter lambda means wavelength. So if we want to find the frequency, we'll first start with the formula C equals lambda nu, and then rearrange it. Nu, which is the frequency, is C divided by lambda. So that's going to be 3.00 times 10 to the power of 8 meters per second, the speed of light, divided by our wavelength. Now the wavelength was 213 nanometers. I need to put it in here in meters. So using that data booklet, page 2 at the bottom, if I need to, nano is 10 to the minus 9 meters. So 1 nanometer is 10 to the minus 9 meters. So I'm just going to tack on times 10 to the minus 9, and then instead of nanometers, my wavelength is now in meters. I'm going to grab my calculator. I'm going to make use of the scientific notation button on the calculator. On the graphing calculator, it's right above the comma button. On other calculators, it'll be a button that says EE or possibly EXP. That's used for scientific notation. So 3, and then we press that button, 3 times 10 to the power of 8, and then we divide by 213. We press that button again, times 10 to the power of, and negative 9. And then equals 1.41, we round it off to 3 significant digits, times 10 to the power of 15, E15, at the very end. So 1.41 times 10 to the power of 15. Notice the meters cancel, and we're left with per seconds as the unit for frequency. Remember that frequency can also have units called hertz, and they're the same units as per second. Now we want to calculate the energy of the radiation. To do that, we'll use Planck's equation, and we could use either E equals h nu, since we now know the frequency, or E equals hc divided by lambda. I'll use E equals h nu here. So h, Planck's constant, times the frequency. So Planck's constant, very, very small number, 6.626 times 10 to the power of minus 34 joule seconds, times the frequency, which we just found, 1.41 times 10 to the 15 per seconds. Now you remember that on my test I expect to see the formulas, I expect to see numbers put in with their units, and then the answer with its units. So again, we're going to use that scientific notation button. So 6.626 scientific notation times 10 to the power of negative 34 times 1.41, the scientific notation button, times 10 to the power of 15 equals 9.34 times 10 to the negative 19. 9.34 times 10 to the power of negative 19. The seconds and the per seconds cancel, and we're left with joules, which is the unit for energy. Alright, now you could also say joules per quantum, or joules per photon if it were visible light. Question number 2. This is one of the harder problems in the first unit mathematically. An electron falls from level 6 back to the ground state in a hydrogen atom. Calculate the wavelength of electromagnetic, EM, radiation that is emitted. If an electron falls from a higher level back down to a lower level, it will always emit energy, release energy. If it were to move from a lower level up to a higher level, it's going to have to absorb energy. So the question says, what wavelength of radiation is emitted because the electron is falling? It's going to emit, release radiation. So let's calculate the wavelength. This is a hydrogen atom, and we know that the ground state in a hydrogen atom, the lowest energy level state for the electron in hydrogen, would be n equals 1. So I'm going to just think of this as n equals 1. So we're falling from the 6th energy level, n equals 6, back to the lowest level, the ground state for hydrogen, which is n equals 1. So there's 3 steps to the problem. Step 1, we're going to calculate the energy in level 6 and in level 1, the starting energy and the final energy. So E6, I'm going to use Bohr's energy equation from my data sheet, formula sheet, negative 2.18 times 10 to the minus 18 times, and Bohr's equation says z squared over n squared, where z stands for the atomic number of the element, and n is the energy level that we're dealing with. So for level 6 in hydrogen, that'll equal negative 2.18 times 10 to the minus 18 times, for hydrogen, the atomic number z on a periodic table, if you don't know that, is a 1, so 1 squared, over the energy level, which is 6 squared, and that's going to equal, grab your calculator, again using that scientific notation button, negative 2.18 times 10 to the power of negative 18, and then times 1 squared divided by 6 squared. I'm just going to divide that by 36. 6 squared is 36, equals negative 6.06 times 10 to the minus 20. So negative 6.06 times 10 to the negative 20 joules. That's the energy of the electron in the 6th energy level. It fell back to the ground state, which we said was the first energy level. So now let's calculate E1. It's going to equal negative 2.18 times 10 to the minus 18 times, it's still hydrogen, so the atomic number is still 1 squared, but now the energy level is level 1, so 1 squared. And then we can just do some mental math right there. 1 squared, 1 squared. That's not going to change this number. So negative 2.18 times 10 to the minus 18 joules is the energy of level 1. The second step of the problem, now that we know the energy you started with and the energy you finished with, we're going to find the change in energy, delta E, as the electron falls from level 6 back to level 1. Now technically, this change in energy will come out as a negative number because we're losing energy. Energy is emitted. But I'm going to just want to know the absolute value of that. I'm going to want to know the positive amount of energy released. Technically, when you find a change in something, you should always do the final level, so E1, that's where the electron finishes, minus the starting level, E6. So absolute value of negative 2.18 times 10 to the minus 18 joules minus negative 6.06 times 10 to the minus 20 joules. Now in my experience, this, even though it's a relatively simple thing that we're doing here, many students screw this up. I think it's the minus negative that they just forget to do on their calculator, and so they just do this incorrectly. So just be very methodical as you're typing in on your calculator. So negative 2.18 times 10 to the minus 18, subtract negative 6.06 times 10 to the minus 20. And just quickly look, minus a negative, that looks right, equals negative 2.12 times 10 to the minus 18 joules. But we're going to make that positive because we're taking an absolute value. So the absolute value of delta E is positive 2.12 times 10 to the minus 18 joules. Again, just understand what this meant. It was a negative change in energy because energy was being emitted, released. But we don't really want the negative value, so we're just asking how much energy was released. When we ask how much energy was released, it makes that number positive. Okay? So we want the absolute value. The third and final step is to use Planck's energy equation. His equation said E equals hc divided by lambda. I'm using this form of his equation because we're going to find the wavelength. Let's rearrange the equation to say lambda equals, if you multiply both sides by lambda, you'd get E times lambda equals hc, and then to get lambda by itself, you'd divide both sides by E. So lambda will equal hc divided by E. And this E is going to be our delta E from the previous step. So equals 6.626 times 10 to the minus 34 times 3.00 times 10 to the 8. I'm being a little lazy there, leaving out my units, divided by the energy 2.12 times 10 to the minus 18 equals, now because this is a wavelength, you know what, I'm going to go back and put my units in. Joule seconds, meters per second, and joules. So the joules cancels out, the seconds and the per seconds cancel out, we're left with meters, which makes sense because we're finding a wavelength. So on your calculator, 6.626 times 10 to the negative 34 times 3 times 10 to the 8 divided by 2.12 times 10 to the negative 18. The energy released is the wavelength released 9.38 times 10 to the minus 8 meters. Okay, now if you wanted to know what that is in nanometers, we don't need to do this. It didn't ask nanometers, but if it did, we would just set up one quick unit multiplier, 9.38 times 10 to the minus 8 meters, and we can convert meters by getting rid of it like that to nanometers, and then using page 2 of our data booklet, we remember that 1 nanometer is 1 times 10 to the minus 9 meters. Dividing those two numbers, we would get, let's see, 93.8 nanometers. Okay, you did not need to do that, but if you did, if you were asked, that's how you might set it up with a unit multiplier. Alright, pause the video, see if you can match the concepts on the left with their descriptions or definitions on the right. So this is straight out of our notes. Heisenberg's uncertainty principle, which is at the heart of the new model of the atom, said it's impossible to know both the position of an electron and its momentum. The momentum is similar, not exactly the same, but it's related to velocity of the electron. So those two go together. The Aufbau principle, this is used whenever you draw a Bohr diagram in grade 11 chemistry, or when we draw orbital diagrams and electron configurations. We always start at the lowest energy level, fill it, and then move to the next level, fill it, and move to the next highest level. So we're always starting at the lowest energy levels and building up. So that's the Aufbau principle. Pauli's exclusion principle. If you're studying AP chemistry or college chemistry, technically it deals with something that we skipped over in grade 12 chemistry. It deals with quantum numbers, and it actually states that no two electrons in an atom can have the same 4 quantum numbers. But the result of that is what we studied. It means that orbitals can hold a maximum of just 2 electrons, and they have to have opposite spins. So for us, in grade 12 chemistry, that's what we would connect the Pauli exclusion principle with. Hund's rule is when we're drawing orbital diagrams and we're filling up a p subshell or a d subshell or maybe an f subshell. We have orbitals of equal energy in those subshells, and Hund's rule says keep the electrons in those subshells unpaired as long as possible. In other words, when every electron has one unpaired electron, then and only then would you start pairing them up within a subshell. Question 4, see if you can describe for yourself the difference between a ground state and an excited state for an atom. Okay, the ground state is what happens when you obey the Aufbau principle. You end up with all of the electrons in an atom in their lowest possible energy levels. That's the ground state for the atom. If you don't obey the Aufbau principle, you'll place electrons in the wrong energy levels. They'll be in higher energy levels than they should be. You have an excited state. So excited states would be where one or more electrons are found in higher energy levels than they should be in the ground state. Now, the periodic table, we know, is connected to the new model of the atom because we can break it up into what's called an S, P, D, and F block. In other words, S, P, D, and F are the different orbital shapes, the different sub-levels, and they match regions on the table. So see if you can identify where the S, P, D, and F blocks are on the table. Right, so the S block is the first 2 columns. So this is the S block here. First 2 columns of the table, including helium. Helium over there is part of the S block. The P block is this section over here, these 6 columns. That's the P block of the periodic table. Now the number of columns is important, right? The fact that there's only 2 columns in the S block is because to fill the S sublevel, you need only 2 electrons. The fact that there's 6 columns in the P block is because to fill the P sublevel, you need 6 electrons. The D block is here in the middle of the periodic table. It's the transition metal elements. So everything in the middle, from here to here, all of that is the D block. And if you counted the columns there, you'd find there's 10 columns. It takes 10 electrons to fill the D block. The F block is this section at the bottom of the periodic table. It's the rare earths, or the lanthanides and actinide series. That's the F block at the very bottom of the table. And we don't get there very often in grade 12 chemistry. In fact, I don't think you've ever seen an example where you needed to use the F block. So here is a periodic table. Okay, if you want to use your own table, you could do that. We want to talk about periodic trends. So this is the last topic in the unit, where we looked at different properties. We talked about atomic radii, the radius of different atoms on the periodic table. Radii, you remember, is just a plural form of radius. So if you have one atom, it has a radius, and if you have two atoms, you can talk about radii. So which of the two atoms, magnesium or barium, have the smaller radius? That would be a periodic trends question. Further down, we see a question about first ionization energy, which was another periodic trend. First ionization energy, can you just pause the video and see if you can define that for yourself? Okay, did you say that first ionization energy is the energy needed to remove a valence electron, the first valence electron technically, from a ground state atom in the gas phase? That would be the first ionization energy. If you're going to remove the valence electron, or any electron, you have to put energy into the atom to take away its electron. So the first ionization energy, you're removing the valence electron from a ground state gas phase atom. There are trends that we looked at on the periodic table for that as well. And so a question like this, which is the larger first ionization energy, sodium or cesium, is a periodic trends question. The third property that we looked at was electronegativity, and that's actually, you have this table in your data booklet, so you don't need to memorize that trend. Can you take the periodic table above and imagine what is the trend in atomic radius as you go across the table? What's the trend as you go down at the table? So across a period and down a group. What are the trends in the radii of atoms? Let's pause and see if you can remember that. So when you go across the table, we said in our notes that atoms get smaller. When you go down the table, when you go down a group, atoms get larger. The trend in first ionization energy, a good study trick is simply to remember it's the opposite of atomic radius. So when you go across the table, first ionization energies get larger when you go across a period. When you go down a group, the first ionization energies get smaller. All right, with that understanding, which has the smaller radius, a magnesium atom or a barium atom? Well, magnesium is here on the table, and barium is down below it. So when you go down the periodic table, down a group, atoms get larger, so therefore the smaller atom was magnesium. So magnesium is smaller. Maybe I should only circle the answer here. Which has a smaller radius, aluminum or argon? Well, aluminum is here in period number 3. Argon is here, also in period number 3. And we remember that when you go across the period like that, left to right, atoms get smaller. So the smaller radius there would be argon. The first ionization energies, sodium or cesium, which is larger this time. So sodium is here, and cesium is here. Now the trend in first ionization energy is the opposite of atomic radius. When you go down the family, the first ionization energies get smaller. So the larger first ionization energy would be sodium between those two. Which is a smaller first ionization energy, potassium or bromine? Potassium is here, Bromine is in the same period, it's over here, and the trend is the opposite of radius. First ionization energies get larger when you go across the period, so bromine would have the larger one, and potassium would have the smaller one. Now you were requested to explain why for each of those. If you were asked to explain, you would not simply state, as I just did, that the trend is to get smaller or larger. You'd have to go a little deeper than that. So let's just quickly try to explain for atomic radius why atomic radius shrinks when you go across. The explanation deals with, number one, the fact that the valence electrons for the atoms are found within the same energy level. So if you're hydrogen to helium, the valence electrons are in level 1. Lithium to neon, those elements, their valence electrons are in level 2. Sodium to argon, they're in level 3, etc. Now that we've established the valence electrons are in the same energy levels, we note that as you go across the table, each next element has one more proton. So the nuclear charge, the positive charge in the nucleus, gets larger and larger and larger. With more positive charge pulling on the valence electrons, they get pulled closer and closer to the nucleus. And that results in two things. If the valence electrons are being pulled closer to the nucleus, the atomic radius is going to get smaller when you go across the table. Also, if the valence electrons are being pulled with more and more positive charge from the nucleus, it's going to be harder and harder as you go across the table to remove the valence electrons. So the first ionization energies will increase. So we've just explained the trends in first ionization energy and radius when you go across a period. What about when you go down a group? Well, there, the first thing we notice is that when you go down a group, the valence electrons are not in the same principal energy level. Hydrogen is in level 1, but lithium's valence electron is level 2, level 3 for sodium, level 4 for potassium. And we remember that when the energy levels increase, the electrons with more energy are found further and further from the nucleus. Therefore, the atomic radii are going to get larger and larger when you go down the table. But you might, if you're a very careful observer, notice that there's also more and more protons. There's greater and greater positive charge. And so you might ask, well, doesn't that create larger and larger attraction? And that might counteract the greater distance of the valence electron from the nucleus? That's a good observation, but the answer actually is no. And the reason for that is that the valence electrons are shielded from the nucleus. So if you have a nucleus of, let's say, potassium, which has 19 protons in its nucleus, it has one valence electron and it's out here. Let's just call that the valence electron. Between that valence electron and these 19 protons, there are 18 other electrons between those two. So these 18 negative charges shield the one valence electron in potassium from the nuclear charge, most of it. So instead of feeling 19 protons, this one valence electron ends up feeling just a little bit more than one electron, really. So because it's of shielding, the valence electron does not feel that full nuclear charge. So as you go down the family, the valence electrons are found in energy levels that are higher and higher, further and further from the nucleus. They're also shielded from the nuclear charge. Therefore, the atoms are going to get larger and larger as the valence electrons are further and further from the nucleus. And because of that increased distance, the valence electrons become easier and easier to remove as you go down the group. So the first ionization energies get smaller. All right, the last question on this page is a bit trickier. See if you can pause the video and answer this. This is selenium 2-, rubidium positive, and krypton. We want to rank those things in order of decreasing radius. did you notice, looking at them on a periodic table, I've got a electronegativity table here, but it'll work. Selenium is here, krypton is here, but we didn't have just selenium, we had selenium 2 negative. The 2 negative means that it added 2 electrons. So selenium 2 negative actually has the same configuration as krypton. The other element was rubidium positive. Rubidium is over here, element number 37. But if it's positive, it lost one of its electrons. So instead of 37 electrons, it has just 36. And that means rubidium positive also looks like krypton. So all three of these species look, in terms of their electron configurations, like krypton. The word we used in our notes was to say that they are isoelectronic. And that's just a scary looking word, which means they have the same electron configurations. Now, why is that an important thing to note? If their electron configurations, their electron clouds, are identical, then the only thing really differing between these three things is their nuclei, the positive charge in the nucleus. Krypton has 36 protons, 36 positives, rubidium has 37 positives, and selenium has only 34 positives. So they have the same electron clouds, but look at their positive charge in the nucleus. Can you now reason out which one of those things would be the largest, which one would be the smallest? We're going to put them in order of decreasing radius, so the largest down to the smallest. Which one would go first? Well, the largest one would be the one with the smallest nuclear charge. So that would be Se2-. The rubidium with the greatest positive charge is going to pull the electron cloud closest to the nucleus, and so it's going to result in the smallest of the three atoms, and krypton is going to be in the middle because it had the medium number of protons. Alright, so there you've got, that's periodic trends. Now, in addition to the first ionization energies, we also discussed successive ionization energies. And here we're looking at the first, the second, the third, the fourth, etc., until you've removed all of the electrons from an atom. So see if you can look at this graph, which shows number of electrons removed on the x-axis versus ionization energies on the y-axis. How many valence electrons does that atom have, and which element would it be? Alright, the key to remember is that the first electrons removed are the valence electrons. So these 3 electrons right here represent the 3 valence electrons. So there's 3 valence electrons. And I know there's 3 because after the third electron was removed, the ionization energy jumped very high. And that's because, if you think of the Bohr model for this, in fact, let's just we'll come back to that. If you count here, there's 8 electrons, here there's 3, and up here there's 2. So these 2 are the highest ionization energies because they were closest to the nucleus. These 8 are next because they're in a second shell, a second energy level, and these 3 are the valence electrons in the highest energy level. They're the easiest ones to remove. They have the lowest ionization energies. So in a Bohr model, this thing would have had 2 electrons in the first energy level, 8 electrons in the second energy level, and 3 electrons in the valence energy level. So in all, it has 13 electrons, and if you looked at a periodic table, the element with 13 electrons is aluminum. Alright, pause the video now and see if you can do some electron configurations, noble gas configurations, orbital diagrams as well. So the ground state electron configuration. You might want to have a periodic table with you when you do this. Okay. I'll just write it out here. Aluminum has, we just kind of discussed it here, it's got 13 electrons, so 1s2, it's got 2 electrons in the 1s sublevel, 2s2, 2 electrons in the 2s sublevel, 2p6, 6 electrons in the 2p sublevel, and notice 2 plus 6, there's the 8 electrons that were in the second energy level, and then finally 3s2 and 3p1, there are the 3 valence electrons that were in energy level 3 that we just discussed a moment ago. Now chromium, I remember, is an exception to the off-bell principle. When you start at the lowest level and build up like this, chromium is a bit of an exception. So we remember that. It has 1s2, we're looking at a periodic table. This is my electronegativity table, but it'll work. We're starting up here at hydrogen, 1s, and helium, 1s2, and we're going to go across the table until we hit chromium. And we remember that for chromium, we're in period 4, so it's going to have 4s, and then we're going to go into the 3D subshell. So this is 1s, this is 2s, right here, lithium, beryllium, 2s. Over here is 2p, and then 3s, 3p, argon, and then 4s, potassium, calcium. And after 4s, we remember we go to 3d, in the D D block of the periodic table. So for chromium, 1s2, 2s2, 2p6, 3s2, 3p6. At this point, I've reached argon on the periodic table. Now you would think that chromium should be 4s2 and then 3d4. But in fact, it's an exception. One of the 4s electrons jumps to the 3d subshell. So instead of 4s2, you're left with just 4s1. And instead of 3d4, you get 3d5. And it ends up with 6 unpaired electrons in all, 5 and 1. For noble gas abbreviated configurations, we recall that in this electron configuration, much of it, in fact everything up to there, was a noble gas. That represents argon on the periodic table. So when we abbreviate the configuration with a noble gas configuration, abbreviated form, we simply use the symbol of the noble gas to represent all of this, and we add on the extra bit. So if we want tin's electron configuration abbreviated, we find tin on the periodic table, and we go to the noble gas that was before tin. So if tin is element number 50, the previous noble gas would have been krypton, which is element number 36. So for tin, I'm going to say krypton, square brackets. So we're saying that krypton's configuration plus some extra bit. Now what is the extra bit after krypton? Well, after 36 would come rubidium and strontium. Now that's 1, 2, 3, 4, that's 5s. Then this would be 4d, and then 5p. So krypton, 5s2, 4d10, and then 5p2. Tin was the second element in the p block in row 5. Nickel, the previous noble gas before nickel was argon, so Ar, square brackets, and then we have to add on to that 4s2, and then we're going into the D block in row 4, so that's 3d, and nickel is element, the 1, 2, 3, 4, 5, 6, 7, 8th element in, so 3d8. Now we're going to draw orbital diagrams for ground state silicon, ground state copper. And as soon as I see copper, if I've prepared, I remember that copper is like chromium. It's an exception to the off-bow principle, and it does the same thing. a 4s electron jumps to the 3d subshell. Orbital diagrams are those diagrams where we use boxes filled with arrows to represent electrons. So for silicon, we think of its electron configuration. It's going to be 1s2. We're using arrows. An up arrow represents one electron spinning one way. The down arrow represents an electron spinning the opposite way. So that orbital now has two electrons with opposite spins. That's the Pauli exclusion principle. 2s2. And now we're going to have to obey Hund's rule because we're going to fill the 2p subshell, and it's got 3 orbitals of equal energy. So we keep our electrons unpaired until each orbital has 1. Then we pair them up. So 2p6, 3s2, and I'll draw the p sublevel, 3p. But for silicon, we're going to need just 2 electrons. So obeying Hund's rule, we'll keep those 2 unpaired. And so we realize it has 2 unpaired electrons, which means it must be paramagnetic. Okay, the question was, is it paramagnetic or diamagnetic? If you have unpaired electrons, 1 or more, you are paramagnetic. If you have no unpaired electrons, these are all paired up, then the element would be diamagnetic. So for copper, we'll do the same thing. 1s2, 2s2, 2p with its Hund's rule. 1, 2, 3, 4, 5, 6, 2p6. 3s2, 3p6, Hund's rule again. Now here comes the exception. Instead of 4s2, it's 4s1, and then instead of 3d, now remember there's 5d orbitals, so 1, 2, 3, 4, 5, 3d. Instead of 3d9, it ends up being 3d10. So 1, 2, 3, 4, 5, Hund's rule, and then 6, 7, 8, 9, 10. So 4s1, 3d10. It has 1 unpaired electron, therefore it is paramagnetic. Okay? If there are no unpaired electrons, it would be diamagnetic. All right, we're getting near the end. The valence configuration is, we remember that valence means the highest energy level. So we want to only include that part of the electron configuration which is on the highest principal energy level. So for barium is in row 6 of the periodic table, so we're only going to include things with a 6 in front of them. So for barium, 1s2, 2s2, 2p6, etc., it's going to end in 6s2. So the only part that's in level 6 is 6s2. Therefore, that's its valence configuration. I'm ignoring everything except what's in the valence level. Antimony, Sb, is in row 5, and so its valence level is level 5. If you look at antimony's position on your periodic table, you'll realize it's going to end in 5s2, 4d10, and 5p3. If you only include the part that was on level 5, 5s2, 5p3. There's its valence configuration. For this next question, classifying bonds, pause the video, see if you know what you're doing. Okay, this is where we're going to definitely need that table of electronegativity values. Make sure you're not looking at your periodic table, but rather the table of electronegativities. To classify a bond as ionic, nonpolar covalent, or polar covalent, we look at difference in electronegativity. Electronegativity is a measure of how strongly an atom attracts the electrons within a chemical bond. Calcium's electronegativity from that table is 1.0 units, 1.0 Paulings. Chlorine's value is 3.0. So from those two values of electronegativity, I can tell that chlorine has a much larger attraction for these valence for the electrons in the bond. This large difference of 2 units, the difference is 2.0 units, tells me that this bond is going to be ionic. When the difference is 1.7 units or larger, the bond is ionic. And what we're saying is that chlorine pulls on these electrons so strongly that it essentially becomes a negative ion, and the calcium ends up becoming a positive ion. Now technically, calcium becomes 2 positive and chlorine 1 negative, but that's because there'd be another chlorine atom bonded to it. For now, just think of it as chlorine becomes an anion, calcium becomes a cation, and therefore you have an ionic bond. Zinc bonded to nitrogen, do the same thing. Find zinc on your table of electronegativities. It's got 1.6 as its electronegativity value. Okay, so I'm just getting these numbers right from the table of electronegativities. Zinc is 1.6. Nitrogen is 3.0. Now, the units are called Paulings, but I don't really care about them for this. The difference in electronegativity between these two would be 1.4 units. Now that's not big enough to be called an ionic bond. To be ionic, you had to be 1.7 units difference or larger. If the difference is between 0.4 and 1.7, we said that that would be a polar covalent bond. Now what does that mean? Nitrogen does have a larger electronegativity, so the electrons in this bond are being pulled closer to nitrogen, but it's not large enough of a difference for nitrogen to just take the electrons. The two atoms are going to share the electrons, so therefore it's a covalent bond. But nitrogen does pull the electrons closer, so therefore nitrogen becomes partially negative. We use a little delta symbol, a lowercase delta, to say partial negative, and the zinc becomes partially positive. So now you've created a covalent bond with a negative and a positive pole, so it's a polar covalent bond. The last example, bromine and sulfur. Bromine's electronegativity is 2.8 Paulings. Sulfur is 2.5 Paulings. The difference here is only 0.3 units. When the difference in electronegativity is 0.4 units or smaller, down to 0, then we call that a non-polar covalent bond. Now when you're subtracting, I didn't specify this, but when you subtract, always just subtract the larger number minus the smaller number. Your differences will always be positive differences. So the non-polar, why? Well, with such a small difference in electronegativity, the electrons are being pulled equally by the two atoms, so they're going to be shared equally. If they're being shared, it's a covalent bond. If they're being shared equally, there's no negative or positive pole created like there was here. So with no poles, no negative positive poles, it's a non-polar covalent bond. So know those 3 classifications based on electronegativity differences. All right. Can you rank these regions of the EM spectrum in order of decreasing wavelengths? Pause the video and try that without looking in your notes. Okay, the different regions of the spectrum: gamma rays, X-rays, ultraviolet light, visible radiation, infrared radiation, microwaves, and radio waves. Visible light can be split into a rainbow. If this is ultraviolet, then at this end is the violet part of the rainbow. This was infrared, so this is the red part of the rainbow. And there's your orange, yellow, green, blue, indigo, and violet. Roy G. Biv. Now, however you memorize this, you need to have that memorized in terms of gamma rays, X-rays, ultraviolet, etc., in this order. Gamma radiation is the short wavelengths. Radio waves, therefore, is the long wavelengths. Wavelengths and frequency are inversely related, so this is the high frequency, this is the low frequency. Energy and frequency are directly related. So if this was a high frequency, it's high energy. That's low frequency, it's low energy. So make sure you've got that memorized, and now this question is easy. We want to do decreasing wavelength, so the longest wavelength going to the shortest. So we want to go longest to shortest, we're going backwards. So of these choices, microwaves would be number 1, which are longer than the next one would be, let's see, a form of visible light, red or yellow. Well, red and then yellow. So microwaves are longer than red, which are longer than yellow. And then at the end, X-rays would have the shortest wavelengths. If you've got that memorized, you can also do something like energies, increasing energies. Do the same thing here. Pause the video. So you want to start with the lowest energy. The lowest energies would be at the same end. So we're going backwards again in that spectrum. So the lowest energy of these choices, UV and gamma, are both over here. So it's going to be one of these visible light colors. It'll be orange followed by blue. So orange is the lowest energy. It's less than blue. And that's less than UV light, which is less than gamma. Gamma is the largest energy, so I've done an increasing energy sequence. Alright, our last page of the review, in 1 hour of review. Decide if the following orbital diagrams are impossible, ground state, or excited states, and explain your reasoning. So here's an orbital diagram as we would normally draw it, with boxes and arrows just side by side. 1s2, 2s2, 2p6, 3s1, 3p3. And right here I see an issue. Normally we would write 3s2 and then 3p2. One of these electrons has jumped from the 3s sublevel over here to 3p. Now it shouldn't be there. So now is that possible or not? Well, yes, it's possible, but because the electron is in a higher energy level than it should be, this is an excited state. Okay, now what would be an impossible state? An impossible state would be an orbital has too many electrons in it, or a sublevel has too many electrons. So instead of 3s2, maybe it said 3s3. Maybe there are 3 arrows in that one box. Instead of 3p6, maybe there was 3p7. That would be impossible. Another impossible situation would be if there was a sublevel that doesn't exist. So for example, if it said 1p instead of just 1s, there is no 1p sublevel, so that would be impossible. This next example is another version of an orbital diagram. This is not how we would normally draw it ourselves, but it's the same idea, except now instead of side by side, the boxes are being put in order of increasing energy like that. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. If you stop and look at a periodic table, that looks like this is the element vanadium, V, and it looks pretty good to me. I don't see anything that's impossible in there, and I don't see any electrons that are in levels that they're not supposed to be in, so this would be a ground state. Okay? Now what if this had been 4s1, and this had been 3d5? 4s1, 3d5. Would that be a ground state, excited state, or impossible? Well, it is possible because, as we said earlier, there would be no sublevel with too many electrons, and there's no sublevel that doesn't exist. So it is possible. 4s1, 3d5. Now that rings a bell. That's the exception for chromium. Chromium, you remember, ends in 4s1, 3d5. Since that's one of the two exceptions that we've memorized, it would still be considered a ground state configuration. That would not be an excited state. Alright, the last example is another way of looking at orbital diagrams. Instead of boxes, there's little lines, but it's the same idea. So 1s2, 2s2, 2p2. I don't see any obvious things that are impossible there, so this would be possible. Is it a ground state or is it an excited state? Well, if you said excited state, you are correct. And the reason that it's excited, as I just misspelled excited, the reason it's excited is because it's disobeying Hund's rule. Hund's rule said when you're filling the 2p subshell like that, you were supposed to keep those electrons unpaired. And the reason for that is that in this situation, when they're paired, they're repelling each other. They really want to get away from each other. So if there's these empty orbitals available, this electron would really like to move to the next orbital. By forcing it to be into this same orbital, it's a higher energy situation, so it's an excited state. Violations of Hund's rule are possible, but they're not ground state situations. The last topic isn't really a question since the answers are right there, but be sure that you're able for the test to identify orbitals by their shapes. So when you see spherical orbitals, we remember that those are s orbitals. As n gets larger, 1, 2, 3, 4, etc., the orbitals get larger and the electrons in them have more and more energy. Okay? The p sublevel, the p orbitals, look like dumbbells or peanuts, and they come in groups of 3 always, so this is on level 2. One of them's on an x-axis, one of them's on a y-axis, one of them's on a z-axis. They're perpendicular to each other. If it showed the 3p sublevel, it would look exactly like these, but it would be larger, in the same way that the 2s is larger than 1s and the 3s is larger than 2s. The 3p subshell would have orbitals just like this, but they'd be larger. The d subshell has 5 different orbitals in it, and 4 of the 5 look like 4-leaf clover shapes, and one of them is kind of a weirdo. It looks like a p orbital, sort of, with a donut around the middle. So if I showed you one of these orbitals on a test question, multiple choice, and asked you, is this an s, p, d, or f orbital, you'd be expected to recognize it. We don't have f orbitals shown here, but we remember that f orbitals simply look more and more complicated than the d orbitals, so I don't have a picture of one there. Alright, so that's the end of this little video, just over 1 hour. We've reviewed most of the things that are on this checklist, but we haven't looked at every single one of them in every possible way, so be sure you do study your notes, make sure you know definitions, practice some of the problems that we did, the math problems. Don't just rely on what was in this video. When you practice them and show your work, don't take shortcuts, you get better and better at it. Anyways, I'll stop there. If you have questions, something that you see that maybe you disagree with, or something in the video that didn't make sense, feel free to reply to the video or send me a question on Edmodo, and I will answer you as best I can. So good luck with your studying for the test or for your exam.